Hi, welcome to the diamond structure. In this video, we're going to talk about starlight and spectra. First of all, we're going to know how the stars glow. For any object that higher than temperature absolute zero, i.e. 0 Kelvin, they will radiate lights but in different wavelengths. It's because two charged particles collide with each other. They accelerate, which means they have changed in their velocities. Then the light radiates away. And the higher the temperature they have, the higher velocity they have. So they are more likely to have higher acceleration, thus the higher energy in light, and higher the frequency the light have. And we called this mechanism Blackbody radiation. It emits continuous spectrum, which means that there would be lights in every wavelength. And according to the graph in the right, you can see that objects of different temperature have different profile of energy distribution. For example, an object that is 6,000 Kelvin is relatively stronger in visible light than in infrared. But for objects that only have 3,000 Kelvin, it's rather higher in infrared than in visible light. Thus, we have an useful relationship between the most intense wavelengths, we call it lambda max, and the object's absolute temperature. And this is called Wien's law. It says that with higher temperature, the most intense wavelengths will be shorter. And this caused a continuous change in the appearance of stars. For hotter stars, it's bluer, and cooler star redder. Next, let's see how the gas affect and interact with the light. For hydrogen atoms, we can assume that the electron orbits the proton in a circular orbit like the Earth orbits. But there are little different from a planetary system like Earth orbits around the Sun, which is the electron cannot orbit the proton in every radii. The distance between the electron and the proton is limited by some quantum mechanisms. We can use the typical formula for circular motion and consider the angular momentum discontinuity. We can obtain different orbiting radii and the kinetic energy for different orbit. For different integer n, the kinetic energy equals to minus 13.6 times 1 over n squared, eV. So, the electron transits between different energy levels, absorb lights or emit lights. For example, an electron transits from n equals to 3 to n equals to 2. The difference in kinetic energy is 1.9 eV, and the corresponding wavelength is about 653 nanometer, and it's blue light. To separate some series of light, we called Lyman series of the light. It starts from n equals to 1 or ends at n equals to 1. And Balmer series start from n equals to 2 or electron drop to n equals to 2. And Paschen line start from n equals to 3 or drop to n equals to 3. Importantly, only the right energy of every transition can make the electrons leave the original orbit to another orbit. So if the light has wrong energy, it will only pass through the atoms and not interact with the atom. Okay, after we know the mechanism of transition in electrons and how the light interacts with an atom. Let me introduce the two different spectra we usually see in astrophysics. They are emission lines and absorption lines. If you look at a blackbody directly, you can see a continuous spectrum with some missing dark lines on it. That's because there are some gas between you and the light source. And the gas atoms absorbs the light, so their electrons can go to a higher energy level. Thus, you will have some missing lines. But if you point your instrument to the gas between you and the light source, you will only get a black background with some lines on it. That's because when the electrons go to a higher energy level, as the time passes, it will probably drop to their original orbit. Then the light emitted away, and your instrument absorbed it. So you will got some lines on your spectrometer. So astronomers use such lines to determine the temperature of a star. For example, the hydrogen Balmer lines are strongest at about 10,000 kelvins. That's because when the temperature is higher, the collision in atoms is stronger. So the electrons will likely go to higher energy levels by collision. So there won't be strong Balmer series, because we say Balmer series is start from n equals 2 or drop to n equals 2. But there are no electrons on n equals 2. What if the temperature is cooler? When the temperature is cooler, the electrons will tend to stay on the ground state, which is n equals to 1. So there won't be any electrons on n equals to 2 to be ejected to other energy levels. So there will not be strong hydrogen Balmer series either. Such mechanisms also happens to single ionized calcium, we call it Ca2. By comparing different lines, we can determine a star's temperature. So, if you know that you have extremely low in hydrogen Balmer series line, but you still have two possible temperature, but you notice the object have a relative strong ionized calcium absorption line, then you can sure that its temperature is about 5,800 Kelvin. And as the temperature getting cooler and cooler, some special lines will appear, such as titanium oxide. This molecule absorbs numbers of wavelengths of light. So you might see some dark bands on spectrum, which means you will see a bunch of lines close to each other on some parts of your spectrum. And why the titanium oxide appears when the temperature gets cold? It's because when the temperature is cool enough, the speed of their particles will not be so fast. So two molecules will bond with each other and become a molecule. By these characteristics like spectrum and the temperature, we can classify the stars. We call it spectral classification. We label the stars by English letter from hot star to cool stars. They are O, B, A, F, G, K, M stars. In this picture, you see the Balmer lines is getting stronger when the temperature gets hotter, but starts to become weak when the temperature is extremely hot. Also, you can see titanium oxide absorption lines in a very cool star like M star. You will see many lines close to each other in the spectrum. But in real situation, we need to know the spectral intensity precisely, so we get a star's spectral energy distribution, which means your instrument will observe the intensity of different wavelengths precisely. Then you can compare different spectra. Overall, it follows the Blackbody radiation as I showed in previous slides. But you can see some caves on the distribution. Then we can know how much the line been absorbed, thus classify the star. Similarly, as extremely cool star like L dwarfs or T dwarfs, more molecules start to appear and absorb lines such as water vapor or methane or iron hydride. When the temperature is cooler, there are more and more molecules appears. This table shows the temperature and the spectral features of different type of stars. Besides the temperature, the spectra gives us more information than you think. If you want to do some research on interstellar medium, which means gas and dust flow in the space, you can also use its spectrum. For example, there are forbidden lines caused by forbidden transitions. They usually don't happen in most of the situation, but under some special circumstances, the electron is excited to a not that stable level, but it can only leave the energy level by collision or excited to another higher energy levels. But the interstellar medium is low in its density and cool enough, so they won't collide that often to excite the electron in the not that stable level. And also, there are not enough energy to excite the electrons away from that not stable level. So they can only radiate light away and go back to relative stable levels. For the notation, we add brackets on the atoms. For example, we add brackets on O3, which means is the forbidden line of double ionized oxygen. And forbidden line of hydrogen atoms also is important in some research. And forbidden lines of hydrogen atoms, also known as 21 cm line, is very important in research of galaxies. The 21 cm line is a good tool to examine the H1 zone and can check the rotation speed of galaxies. 21 cm line is caused by the change of the electron spin. There is only a tiny change in energy, so the wavelength is very long, so it's 21 cm. And molecules can be finely arranged in magnetic field, and those molecules will polarize the light. So you can calculate the strength of magnetic field by looking for polarized light. Astronomers do most studies on spectra because for distant objects, we can only get the light from it. Spectra can tell us more than we think. This is my brief introduction to Starlight and Spectra. If there's any suggestions or questions, feel free to leave in comments. Thanks for listening. See you soon.